Welcome back. We've been talking about a framework for writing numbers in terms of their prime factorization and how that can be helpful. In this video, we'll talk about using prime factorization to find the divisors of a number. When a number is written in its prime factorization, it is straightforward to find all the numbers that divide n. The key idea underlying this principle is that if we have two numbers, a and b, where we've written a as p1 to the e1 times p2 to the e2 all the way up to pk to the ek, and we've written b as p1 to the f1 times p2 to the f2 all the way up to pk to the fk, then a divides b if and only if e sub I is less than or equal to f sub I for all I. Something that's very important to recognize is that in the previous video, we had two different sets of primes. We had a set of primes p1 up to pk and q1 up to ql. But in this example, what we're doing is we're saying that set of primes are the same, and it's possible for the ei and the fi to be zero. Let's look at an example of this. Here's three numbers, A, B, and C. C is kind of big, so I'm not going to say it out. But A is 20,580, and B is equal to 92,588,832. If we write these numbers down in their prime factorization, we see that A is equal to 2 squared times 3 to the first times 5 to the first times 7 cubed. B is equal to 2 to the fifth times 3 to the 10th times 7 squared. And this huge number C is equal to 2 to the 8th times 3 squared times 5 squared times 7 cubed. If we're just looking at these numerical representations of A, B, and C, it would be really hard to figure out which numbers divide which other numbers. But by looking at the prime factorization, determining whether a number divides another is relatively straightforward. What we need to do is we need to compare the powers of 2, 3, 5, and 7. If we look at A and C, we see that the exponent of 2 is 2, and if we look at C, we see that the exponent of 2 is 8. Similarly, if we look at the exponent of 3, we get 1 for A, and we get 12 for C. For 5s, we see that there's a 1 in the exponent of 5 for A, there's a 2 in the exponent of 5 for C, and for the 7s, they both have an exponent of 3. Now, because A and C both satisfy that E sub I is always less than or equal to F sub I for all I, then we know that A divides C. Similarly, we can compare B and C, and we see that indeed 5 is less than or equal to 8, 10 is less than or equal to 12, 0 is less than or equal to 2, 2 is less than or equal to 3, so that means that B divides C. On the other hand, if we compare A and B, when we compare the exponents, we see 2 is less than or equal to 5, 1 is less than or equal to 10, but 1 is greater than or equal to 0, and 3 is greater than or equal to 2. So A does not divide B, and it's also the case that B does not divide A. So we can use this technique to figure out what the set of divisors of a number is, and how many divisors a number has. Here's the technique. Write the number as its prime factorization. N is equal to P1 to the E1, P2 to the E2, all the way up to Pk to the Ek. The set of divisors of n is going to be the set of numbers written as P1 to the F1, P2 to the F2, Pk to the Fk, where F sub I lies between 0 and E sub I for all I. Because of that, we can actually count how many divisors n has. This range from 0 up to ei can be counted by ei plus 1. So the number of divisors of n, if we look at the exponent of p1, it can be anything from 0 up to e1, which has e1 plus 1 possibilities. Similarly, the number of possibilities for the exponent of p2 is e2 plus 1. And we see then that the number of divisors is going to be the product from I goes from 1 up to k of e sub I plus 1. Let's do some examples. If we look at n is equal to 30, which we can write as 2 to the 1 times 3 to the 1 times 5 to the 1, we see that every divisor will have an exponent of 2 that is either 0 or 1. It has to be at least 0 and at most 1. Similarly, the exponent of 3 is either 0 or 1, and the exponent of 5 is either 0 or 1, which means there's 2 choices for the exponent of 2, 2 choices for the exponent of 3, 2 choices for the exponent of 5, which means in total there should be 8 divisors. When we go through and choose all those different possibilities, for example, the exponent of 2 is 0, the exponent of 3 is 0, the exponent of 5 is 0, we get 1. The exponent of 2 is 1, the exponent of 3 is 0, the exponent of 5 is 0, we get 2. And if we continue, we see that the divisors are 1, 2, 3, 6, 5, 10, 15, and 30. And if we put them into a list in ascending order, then we see that the set of divisors of 30 is this set. 1, 2, 3, 5, 6, 10, 15, and 30, and it does indeed have 8 divisors. Here's another example. If n is equal to 5 cubed times 7 squared, or just the number 6125, we see that in the divisors of n, the exponent of 5 can be anything between 0 and 3, so there's 4 choices. The exponent of 7 can be anything between 0 and 2, so there are 3 choices. So we expect there to be 12 divisors. If we go through and we choose all possible choices for the exponents of 5 and 7, we see that indeed there are 12 divisors, and we can write them out as 1, 5, 7, 25, 35, 49, 125, 175, 245, 875, 1225, and 6125. Okay, talk to you soon.